Today we'll be talking about distribution goodness of fits, and our learning objectives are as follows. We're going to discuss and apply two tools we can use to evaluate how well the distribution, we'll say, fits our data, or vice versa. And the two tools we're going to be using are Quantile Plots, and you learned about this in the video. And we're going to also do the chi-square goodness of fit test. Woo. Chi-square goodness of fit test, and that's this funky. I don't think I'll be able to tape it in, but I'll draw it out. Chi-square is like an X, which one of the bars are just going to curve. Yep. So it's a Greek symbol. That's what we're doing today. So let's look at quantile plots. And the kind of standard test that we can use in R for doing this will evaluate where your data fall relative to where they should fall if they followed a normal distribution. But you can make a quantile plot for any distribution. But we're just going to be dealing with normal in this class. So let's take it to the other side of the distribution, like advanced regression. No, it's the same technique, and we're actually going to use a similar approach. We're evaluating quantiles for the chi-square goodness of fit test, and you can do this with any distribution. So making a quantile plot. So what we're doing in a quantile plot is, first I'll just draw this out. We've got X expected, meaning these are the expected values of X, and this is from quantiles of a distribution. And we'll define quantile in a second. And then we have X observed. And these are basically the values of X and where they fall along the probability distribution. So we plot these together on a plot, and if they're linear, you can fit a line to them. If they're linear, then you get, you realize that, okay, well, where they should be along a distribution is about where they fall in terms of the probability of seeing them. And so this plot, if they're linear and they're not like all over the place, this allows us to visually say, well, this is probably fits whatever distribution this is. And R has some built-in functions to do this with a normal distribution. So what we're doing here is we're comparing quantiles of data to quantiles, to, we'll say, theoretical quantiles. If they came from a certain distribution. Which can be any distribution. Okay, so the big question, what is a quantile? Let's take a look, and I'm going to draw something out to kind of help us visualize this. So we'll take a distribution here, function PDF X and f of X, and this will just be some kind of a normal distribution. And what a quantile does is it divides up So divide up distribution into equal areas or probabilities, essentially, right? Because each area in a distribution is a probability at regular percentile intervals. And so if we're interested in, let's see here, 0.125, that is that an eighth? We can really pick any number, but if we want to divide it up into equal areas, we can do that kind of like this, right? We just, each area in this case has about 1.125 of the total area of the probability. And then we get our X values. They're not going to be evenly distributed, right? Because the distribution has different areas. So they're going to be spread out over here. They're going to be closer over here. And so forth. And so a percentile, just to revisit that, a percentile is a value along a distribution with a certain percentage of observations or probability or area below and we've dealt with this already. So the X50 or the 50th percentile is the median, and 50% of observations fall below. So the key to understanding quantiles is that they're going to have different spacing. They're not evenly spaced. And the same goes for percentiles. So if I say the 90th percentile, if I did just like every 10th percentile, right, that would be a quantile where we have between each value, we have 10% of the area of the distribution, or 10% probability, 10% observations. So what this allows us to do then is we say, okay, well, if we had a normal distribution, let's pick a series of X values that are equally spaced in terms of probability or observations. And then let's compare that to where our actual observations fall. Let's talk about how to actually do that. So to make a quantile, so QQ is quantile, quantile. And the two quantiles, remember, this is the expected or theoretical from the distribution, and then this is the observed. So we're comparing the quantiles from our data set to what we would get from a particular distribution. And we'll do this for a normal distribution. So step one is we're going to order observations from our data set, smallest to largest. And these are going to be our Y values, our observation. Then we're going to create a vector of standard normal quantiles. And the way to do this is if we have an observation, say we have n observations, then we want to say, okay, let's chop up the normal distribution in a way that we get the same amount of quantiles to match those. So we have the same amount of x values as we have y values. And to do that, we're going to say, so n is number of observations. We're going to use Q norm. So Q is quantile. And then remember what Q norm spits out. You put information in it, and it gives you what? So D norm gives you the probability density function. So it gives you the density at any point. P norm gives you the cumulative probability distribution. It gives you, so it gives you what you would put into the phi function. The phi function is a cumulative distribution function. So it gives you the z-score. So quantiles under standard normal distribution are just z-scores. So it's just, okay, give me the z value along this. So this is going to be the way to do this. And it's kind of, well, I'm going to write it out in code and we'll talk about it. So we're going to do cum sum, cumulative sum. And then we're going to do rep 1 over n plus 1 times equals n. Just make sure we got enough. I think we need 3 parentheses there. And so what this does is it's going to give us 1 over n plus 1. So let me put that in parentheses there. 1 over n plus 1. This is going to give us the cumulative probability values that we're going to put into Q norm. So Q norm wants to have probability values, and it gives you a z-score. And so what we're doing is giving it probability values, and we're just dividing it by n plus 1 so that we get the equal areas right here. And so we're just going to start with 1 over n plus 1, and then we're going to add it and keep adding all the way until we get to, we should be getting to 1 or just under that. All right, so now that we've got our 2 vectors, we have the order of our observations, we have this cumulative probability vector that gives us cumulative z-scores that are going to be evenly spaced in terms of the area in between them. And then the next step is going to be to plot x from our normal distribution. So we'll just call this x expected, and that's coming from Q norm. And then x observed, where we sort the values. So let's just see real quick. QQ plots. Okay. So what this looks like then is, say n equals 7. We'll have our normal distribution, our z-scores. We're going to chop it up into at 8 different points, but we'll have 7. So we'll have all these different areas, right? Area 1, area 2, area 3. We'll have this rep 1 over n plus 1, which is going to equal just 1 over 8, right? Because it's n plus 1, 1 over 8, 1 over 8. So these are the individual areas in that distribution. And then we do our cum sum. And we get 1/8, 2/8, 3/8, all the way up to 7/8. And then we plug that into Q norm, and that's just going to give us the z-scores. And this is going to be -1.14. 0.5, negative 0.67, all the way up to 1.15. So now this is these are our X values, and then we have our sorted data. And then finally, we can plot these. Actually, I'm not going to make that a new step because I already said that was our step. So we'll get our plot. So these are going to be our z-scores. And it's going to plot, if it follows a normal distribution, it should be fairly linear. And then the last step is to plot this line through it. And the way they do this line is pretty, it's pretty basic. They just pick 2 points and then fit a line to it. So I'll just write out what it is, and then we'll talk about the functions that do it. We can then, the last step is to calculate the slope and intercept of fitted line for the QQ plots. And I'm just going to talk about it. This is what's kind of under the hood when you do these QQ plots together, and we'll do one together. They use the first and third quartile. Throwing a lot of tiles at you. Quartile is quarters. It's a quantile with quarters of the data. And z-scores for the X and Y values. And so that gives us 2 points. And that allows us then to calculate the slope and the intercept. So our Y values are going to be, we can use the quantile function. And that's going to be, we put in our vector of observations, that's X. And then we say calculate the 25th and 75th percentile. So quantile function, you give it a vector and you give it some probabilities. And then it tells you which values fall along those. And if it has to interpolate, it does. And then our X values are going to be from Q, the normal distribution. And we just say, give us the Q normal distribution and find the Z values for 0.25 and 0.75 probabilities. So the slope is just the difference in Y's and difference in X's. And we can use the difference function to do that. So diff Y over diff F X. These are going to spit out, just so you know, it's going to be a vector with 2 values. And so this will just take the difference of the Y's and the difference of the X's and give us the slope. And then the intercept is just solving this equation, y is equal to mx plus b, where b is what we're trying to solve for, is just equal to the first y value minus the slope. So this is equal to m times the first x value. So the brackets, if we have a vector, and so x is a vector with 2 values, whenever we do the brackets, this tells us what index to choose from that vector. So if I do x1, it's just going to give me this first value. If x had 10 vectors in it, then I could just do whatever index I want to put in there, and it's going to spit out that value. So the brackets work for vectors, they work for matrices, they work for data frames, but for data frames you can also do the $sign and find a particular column. So okay, so let's look at some quantile plots. Here are some quantile plots with distributions with different skewness. And so what they did is, here is the underlying distribution that the sample came from. Here is a perfectly symmetrical distribution. Here is a negatively skewed distribution, and then, or sorry, positively skewed and then negatively skewed. And then here is the QQ plot, I think for the normal, that shows us how it looks. So with a perfectly symmetrical normal distribution, then we have essentially perfect overlap, perfectly linear. But as we get different skewness, you start to see this divergence from that straight line. And so as we get more positively skewed, then we get this kind of concave upwards type of look. And then for negatively skewed, we get this concave downwards type of look. So this will tell us, if we start to see these divergences from the line, we can interpret it in a certain way, like, oh, well, maybe it's a skew distribution. Maybe we need to think about log normal or some other distribution that can fit skewness in it. So I pulled up the goodness of fit QQ plot R scripts that I have on Canvas. And what I'm doing here is going through the steps that we talked about to make a QQ plot. So the first thing we're going to do is just plot a normal distribution. Standard normal distribution. So z-scores centered on 0, standard deviation of 1. And then I'm creating this sample here where n is equal to 10. I'm setting up the percentile. So here's the rep n over n plus 1 cum sum. So this is where we're going to evaluate the standard normal variable based on, or z-scores based on a sample size of 10. And so here's our percentiles. They don't go all the way up to 1, right? They're just kind of cutting along that, so we get symmetrical areas in between. I'm using Q norm with those percentiles to get my z-scores. So these are my quantiles right here, just symmetrical z-scores. And then I'm going to use this function to actually plot those quantiles along the normal distribution. So you can see how they're not super symmetrical. This area is equal to this area, is equal to this area, and so forth. So they kind of get denser the closer in you get, because it's just more probability in between. Segments is a function that plots line segments from point A to point B. Okay, here we're going to do the same thing, but for the cumulative distribution function. And you can see how these are equally spaced, right? Equal probability in between on the cumulative distribution function, but these have that same cluster or increasing of density. All right, so let's do this. We're going to take a random sample from the normal distribution. So a mean of 20, standard deviation of 4. We are going to create a sample and then take a mean and a standard deviation of that sample using our norm. So this is my random sampler. Here's a histogram of that sample with frequency equals false. That gives us the density. And then we're going to plot the normal distribution over that with the same mean and standard deviation. I'm going to make that a little bit of a thicker line, so I can see that. There we go. There's our sample. There is the normal distribution from which it was sampled. You'll notice that I do this little set seed function. That means that every time you run R norm and get that sample, it's going to be the same sample. If you run R norm every time, it's going to give you a different sample unless you set the seed, which is kind of like the random number generator thing. So just a little note there. Okay, now we're going to go through the process to make a QQ plot. First, we're going to get the length of our sample, n. I've already set that up here, but here you go. So n is 25. And then I'm going to sort it and it's from small to large. I'm going to do that p-tile thing and then get my z values based on that sample. So now I have a lot more z values, right? It's going to go all the way from negative 1.76 all the way up to 1.76. And then we can create that QQ plot. So now all I did was I just plotted the x values, which is the z-scores, along the quantiles, my sorted x values for my observations. And then we're going to fit that line. So first we're going to get our y values based on the observations. The 25th and 75th percentile, we're going to get our x values, which is from the q norm function, the z-scores, calculate the slope and the intercept. And then we can use this AB line function to just plot a line. So you say A is the intercept, B is the slope. This is just y is equal to, well, you know what I'm saying. It gives you, if you give it two parameters, the B is the slope and A is the intercept, it'll plot a line on a plot. So that's the fitted line right there. Yeah.
You got any chance to know how to create those curved lines that tell you whether or not the points straight or away from the direction?
Well, we're gonna oh yeah, residuals. We're not gonna talk about that until later. We'll talk about regression. Yeah. Okay. Ooh. Just clear that. So I'm gonna just go ahead and do this again. Okay, so we went through all these steps. We talked about how you do this, like step by step. And then I'm going to give you the same functions in R. So the functions in R to do this just without all the steps, I just want to kind of look under the hood, is QQ norm. You give it your sample, and then you can tell it some plot characteristics, and it's going to give you a plot. So it's the same exact plot. And then QQ line, you give it your x values, and it will do the same steps that we just did. So we get exactly the same plot, and this is just a built-in function in R. QQ norm gives you the plot, QQ line gives you that fed line.
There's no special library required to use QQ.
No, just the base library in R.